Hello, everyone. Today is our 20th graduate seminar, Grad Talk seminars, and today we have a guest, Dr. Gabriel Hanna'ya from Canada, Alberta. Good morning, Dr. Gabriel.
Good morning, Murat.
Accepting our invitation. And I want to make a brief introduction for you, and then we can start the seminar. Dr. Gabriel received his bachelor degree in chemistry from Laurentian University and PhD in chemistry in the University of Toronto. And his PhD research focused on the development and application of mixed quantum classical algorithms for simulating proton transfer reactions in condensed phased systems. And he was a postdoctoral researcher for 3 years in Michigan University, Ann Arbor. In Michigan University, he worked on a mixed quantum classical methodology for simulating multidimensional infrared spectra. And after that, in 2009, he joined the Department of Chemistry at the University of Alberta, Canada. Thank you, Dr. Gabriel Hanna'ya. Now we are with you for your nice seminar. Thank you.
Thank you very much, Murat. So I'd like to begin by thanking the Graduate School of Science and Engineering at YTÜ for the invitation to give such an honored grad talk. So it's truly an honor to give such a talk to graduate students from a wide range of backgrounds in both science and engineering. So today I'll be talking to you about a research area that I actually started working in as a PhD student at the University of Toronto, and that I still work in amongst other areas. So given the broad audience, today's talk will give a general overview of why and how one would mix quantum and classical mechanics for the purposes of molecular modeling. Okay, so before I begin, I'd like to show you where I'm from. So I'm from the University of Alberta, which is in Edmonton here. It's the capital city of the Western Canadian province of Alberta. And to the right, here's a picture of our main campus. And the chemistry department, which I'm a part of, is situated in this building here. And below, you can see views of downtown Edmonton from the river valley in the summer and in the winter. Okay, and here's some pictures of my research group. On the left is a picture that we took during a group meeting on Zoom this past summer. And on the right is a recent picture of our first in-person meeting since the beginning of the pandemic. Okay, so on to the outline of my talk. So I'll start by contrasting classical and quantum mechanics. Then I'll give a brief overview of molecular simulation. And next, I will get into some detail into the subject of this talk, which is mixed quantum classical dynamics. And finally, I'll present an application of mixed quantum classical dynamics related to heat transport in a single molecule junction. Okay, so depending on the speed and size of a system, physics could be roughly divided into 4 main domains. So classical mechanics, quantum mechanics, relativistic mechanics, and quantum field theory. In this talk, we'll focus on classical mechanics, which applies to systems that are far larger than 10 to the minus 9 meters, and whose speeds are far lower than the speed of light. And we'll also focus on quantum mechanics, which applies to systems that are near or less than 10 to the minus 9 meters, and whose speeds are far less than the speed of light. As you'll see later in the talk, we'll draw special attention to the boundary between classical and quantum mechanics. So classical mechanics is a pre-20th century theory, which was developed by the likes of Newton, Jacobi, Lagrange, and others. So it describes the motion of macroscopic objects from small particles all the way to planets, stars, and galaxies. And in classical mechanics, if the initial state of a system is known, it is possible to predict its state in the future, making classical mechanics a deterministic theory. On the other hand, Quantum mechanics is a 20th century theory, which was developed by the likes of Bohr, Planck, de Broglie, Born, Einstein, Schrödinger, and many others. So it describes the motions of atomic and subatomic particles. In quantum mechanics, even if the initial state of a system is completely known, it cannot predict with certainty what will happen in the future, but can only give probabilities. In this sense, quantum mechanics is a probabilistic theory. So to give you a sense of why quantum mechanics is a probabilistic theory, I would like to read to you the following quote by Dirac. So Dirac states, "There's a limit to the fineness of our powers of observation and the smallness of the accompanying disturbance, a limit that is inherent in the nature of things and can never be surpassed by improved technique or increased skill on the part of the observer." In other words, when performing measurements on very small objects, such as atoms and subatomic particles, a non-negligible disturbance is inevitable, and no improvement in the experimental method will make the disturbance negligible. So depicted here is an example of such a measurement. In this experiment, photons are used to observe an electron, but after the observation, the trajectory of the electron will not be known with 100% certainty. Since when one repeats the measurement, one finds that the electron follows another trajectory. Therefore, the act of measurement, in this case, the shining photons on the electron, destroys the determinism of the electron. So classical mechanics, a deterministic theory, is therefore not suitable for describing the dynamics of small objects. One must resort to quantum mechanics, which gives the probability of observing a particular result. In this case, the probability of observing the electron here or here or here, and so on. Okay, so now let's enter the quantum world. So here's a picture from an old Physics Today article by Zurich, which nicely depicts the boundary between the classical and the quantum worlds. As you can see on the right here, the classical world is the world we are accustomed to seeing, where everything is well defined. However, when one crosses the border into the quantum world, things become fuzzy, as you can see, or less certain. Particles begin to behave as waves and vice versa, and systems can exist in so-called superposition states, like the cat, which is depicted here, being both dead and alive. So let me now elaborate on one of the most notable and important phenomena in quantum mechanics, so-called wave-particle duality. So wave-particle duality is the notion that every quantum entity may be described as either a particle or a wave. The most famous experimental demonstration of wave-particle duality is the famous double slit experiment. In this experiment, electrons are fired one at a time through a double slit, shown here, and ultimately impinge upon a screen. And over time, an interference pattern emerges with light and dark fringes, as you can see here. Such an interference pattern could not have been produced if the electron did not behave as a wave. So quantum mechanics explains this phenomenon by saying that electron could go through this double slit or through the two slits simultaneously. Mathematically, this is represented by writing down the so-called wave function, this capital psi here, Greek letter psi, as a superposition, or more specifically, a coherent superposition of the electron going through slit 1, so that's psi 1, plus psi 2, which corresponds to the electron going through slit 2. As a result, the probability density, which is defined as basically the square of the wave function, has an interference term. So that's this 2 psi 1 psi 2 star that you see here. And without this interference term, one cannot observe this interference pattern on the screen. So if the electron were not in a coherent superposition of states, as shown here, you'd only see the blue pattern, which is shown here. So with some density behind each of the slits. So this would be due to the electrons just diffracting classically from one slit or the other. So here's another experimental demonstration of the double slit experiment, this time with cold rubidium atoms. So rubidium is much heavier, or rubidium atoms are much heavier than electrons. So as can be seen here, it is possible to generate an interference pattern even with much heavier particles, albeit at very cold temperatures. So now, focusing on the picture on the right, when the left slit, so in the left slit of this experiment, is irradiated with microwave photons, the coherent superposition of states that the rubidium atoms were in is destroyed. So as you can see, we have the classical pattern emerging. So this process by which the coherence is lost and classicality, if you wish, is approached is known as decoherence. Okay, so now that we've briefly introduced classical and quantum mechanics, let's move on to talk about molecular simulation. So simulation is one of the three components or pieces needed to achieve scientific understanding, the other two being theory and experimentation. So these components are all interconnected and can inform one another. So simulation is extremely important for several reasons. So except in very simple cases, there are no analytical solutions to most real-world problems. In many cases, experiments may be too difficult, if not impossible, or they may be even too expensive to perform. So simulation is needed to understand experiments. It can also inspire new experiments. And finally, the results from experiments can also complete theories. So as many of you already know, molecular simulation is widely used across many domains in science and engineering. Here's a listing of just a few domains. So from chemistry to physics, biochemistry, pharmacology, material science, chemical engineering, mechanical engineering, and the list goes on. So here's a list of the main classes of simulation methods that are used to study both the structure and the dynamics of molecular systems. So on the left here are some methods or classes of methods that are used to study structure, molecular structure. So Monte Carlo, electronic structure methods, quantum mechanics, molecular mechanics, or QMMM. And on the right, here are several classes of methods that are used to study the dynamics of molecular systems. So classical molecular dynamics, coarse-grained molecular dynamics, ab initio molecular dynamics, semi-classical dynamics, mixed quantum classical dynamics, and finally quantum dynamics. So I'm not going to discuss these in detail, but in this talk, I'm just going to focus on mixed quantum classical dynamics. Okay, so an important consideration when deciding on which simulation method to use is the length and timescales involved in the system under study. So here's a picture depicting the various scales. So from the quantum scale, which involves sub-femtosecond to picosecond timescales, and sub-picometer to nanometer length scales, one can, to the mesoscale up here, which involves microsecond to millisecond timescales and micrometer to millimeter length scales. So from the quantum scale all the way up to the mesoscale, one can find appropriate simulation methods for the problem at hand. So in this talk, we're going to focus on the quantum scale, or classes of methods that are appropriate to the quantum scale. So another consideration is what type of computer to use for the molecular simulation. A classical computer, such as the IBM Summit supercomputer shown here on the right, or a quantum computer, such as IBM's new Q quantum computer, shown here on the left. So classical computers are the computers that we've been using on a daily basis for many decades. And quantum computers are still in the early stages of their development. So in this table here, or this table here contrasts quantum computing versus classical computing. Let me go through the items one by one here. So quantum computing does its calculations with what are known as qubits. So qubits are, let's say, atomic or molecular systems or ionic systems that can represent 0 and 1 at the same time. So this goes back to the superposition state, or the Schrodinger's cat, the cat that's in a superposition of being dead and alive. On the other hand, classical computing calculates with transistors, which can represent either 0 or 1, not both 0 and 1 simultaneously. Next, the computing power in quantum computing increases exponentially in proportion to the number of qubits. While in classical computing, the power increases linearly with the number of transistors. Next, quantum computers have high error rates and need to be kept ultra cold in order to reduce those errors or the noise. On the other hand, classical computers, as you know, have low error rates and can operate at room temperature. Finally, quantum computing is well suited for tasks like optimization problems, data analysis, and various types of simulations, while classical computing is basically used for everything else. So for everyday processing, they are best handled by classical computers. Okay, now when it comes to quantum calculations in particular, one has to worry about the scaling of computational time with system size. Okay, so on a classical computer, the computational time scales exponentially with the size of the system, making full quantum calculations of molecules with just tens of atoms extremely computationally intractable or intensive. On the other hand, on a quantum computer, the computational time scales polynomially with the size of the system. However, since quantum computers are still in the early stages of their development, we continue to rely heavily on classical supercomputers for performing molecular simulations. So as a result, the approximations to fully quantum methods are needed to reduce computational times. Okay, so as mentioned in the title of my talk, I'm going to now discuss an approximate class of methods known as mixed quantum classical dynamics. So to begin, let's consider a fully quantum mechanical system, such as the one shown here. In many cases, one can decompose the system into a small part, which is the part that we're most interested in, and its environment. So in mixed quantum classical dynamics, the new system of interest is treated quantum mechanically, while the environment is treated classically. In the absence of any interaction between the quantum system and the environment, the dynamics of the system can be described by the so-called quantum Louisville equation, which is shown here on the left. So I'm not going to get into the details of this equation, but just to show you that the dynamics of quantum system is governed by this equation. Okay, and the classical environment, the dynamics of the classical environment is governed by the so-called classical Louisville equation. So you can see that the main difference between these equations look very similar, but the main difference is the bracket. So this bracket here on the left is known as a commutator, and this bracket here on the right is known as a Poisson bracket. So these brackets act differently on the quantities appearing in them. Okay, now, when the quantum system and the classical environment interact, which is typically the case, the appropriate equation is known as the quantum classical Louisville equation, which is shown here. So as you can see, this equation contains both types of brackets. It contains both commutators and Poisson brackets, which is not surprising considering now the hybrid nature of the system. Okay, So since the quantum classical Louisville equation is a differential equation that governs the time dependence of a quantity characterizing the state of the system, one needs to integrate or solve this equation for a given system. So over the years, a host of algorithms have been devised for solving the QCLE. So here's a list of the main algorithms. I'm not going to go through them in detail, just let you look at them. But later, I'll briefly talk about this method known as the deterministic evolution of coordinates with initial decoupled equations. This is a method that we developed a few years ago. So here's a list of important considerations when selecting a mixed quantum classical method for simulating a particular system. So first, the method should properly treat non-adiabatic effects. What do I mean by that? So the method should properly account for the exchange of energy between the system and the environment over the course of the dynamics. Secondly, the method should properly treat so-called decoherence effects. So we talked about decoherence earlier in the talk. Moreover, the method should have a reasonable computational cost and be sufficiently accurate for the problem at hand. So typically, the more accurate the method, the higher the computational cost. So ideally, one should use a method with a favorable balance between accuracy and computational cost. And finally, the method should yield stable long-time dynamics, which is an issue with some of the more accurate mixed quantum classical methods. So in my research group, we're interested in quantum processes involving the transport of particles and energy. So several examples of natural and artificial systems that undergo quantum transport are shown here. So from systems involved in quantum information processing, to light harvesting, to molecular electronics, to nanophotonics and biological systems, one could find quantum transport of energy and particles, they are widespread at the nanoscale. So it turns out that mixed quantum classical dynamics is particularly well suited for studying such processes. So for the case of, let's say, light harvesting, the chromophores could be treated, which basically collect the photons or absorb the photons, would be treated quantum mechanically, while the protein in which these chromophores are embedded would be treated classically, for example. So I will now present an application of mixed quantum classical dynamics to the study of thermal conductance of single molecule junctions, such as the one shown here involving an alkane dithiol molecule between a hot gold scanning tunneling microscopy tip and this cold gold substrate. Okay, so it turns out that measuring the thermal conductance of single molecule junctions is extremely challenging due to the difficulty in detecting tiny heat currents at the picowatt level. So interestingly, however, there are recent experiments on this system, on this gold alkane dithiol gold junction, containing 2 to 10 carbon atoms. And these experiments confirm that the thermal conductance is approximately independent of molecular length, which was previously predicted by some computer modeling. So a simple model known as the non-equilibrium spin boson model has been used to study heat transport in single molecule junctions, such as the gold alkane dithiol gold system on the previous slide. So due to its simplicity, this model has also been used to benchmark approximate methods such as mixed quantum classical dynamics and semi-classical dynamics against exact quantum results. So in this model, the junction molecule is represented by a quantum two-level system, while the thermal reservoirs, the hot and cold thermal reservoirs, are modeled by sets of harmonic oscillators. Now, due to the thermal gradient, heat flows from the hot reservoir to the cold one through this two-level system. Okay? And after some transient time, a steady state heat current is established in the system. So this model is known to exhibit turnovers in the steady state heat current, which is given by J here, as a function of both the system reservoir coupling strength, so and the this delta here, which corresponds to the energy gap in this two-level system. So any approximate method that is used to simulate this non-equilibrium spin boson model should be capable of capturing these turnover behaviors in the steady state heat current, which is established after some transient time. Okay, so we simulated, a few years ago, we simulated the mixed quantum classical dynamics of the non-equilibrium spin boson model using an approach we recently developed known as DECIDE, which stands for Deterministic Evolution of Coordinates with Initial Decoupled Equations. So using this approach, the two-level system is treated quantum mechanically, and the harmonic oscillators in the thermal reservoirs are treated classically. So the first step of this process is to write down the DECIDE equations for the coordinates of the quantum two-level system. So those coordinates are depicted by these little X's here. And also for the positions and momenta of the harmonic oscillators, which are contained in these thermal reservoirs. So I'm not going to get into the details of the derivation of these equations, just to show you that using this DECIDE method, the quantum coordinates are evolved using that commutator bracket that we saw earlier, while the classical positions and momenta are evolved using that Poisson bracket that we saw earlier. So one would write down all these equations for all the coordinates in the system, and next we integrate these coupled differential equations for a given set of initial conditions. Okay. We then continue to generate an ensemble of trajectories starting from different reservoir initial conditions. Okay, so each initial condition will give rise to a trajectory. If you have many trajectories, you have an ensemble of trajectories. And finally, we calculate the property of interest, whatever that property may be, by averaging the relevant time-dependent coordinates over this ensemble of trajectories, which we just generated. So that's the basic process. Now, on to some results. So let's start with the equilibrium case. So in the equilibrium case, the temperature of the left bath or the left reservoir and the right reservoir are equal. So here TL equals TR equals some number 5. And the values of the other parameters in the model are shown here. I'm not going to get into the details. And we used 1 million trajectories in order to generate these results. So for the sake of time, let's just focus on this bottom right panel here. So in this bottom right panel, we plot basically the negative of the heat current as a function of time. Okay, for both the left, so JL is the heat current for the left reservoir, and J right is the right the heat current for the right reservoir. So as expected in the equilibrium case, where the temperatures of the two reservoirs are equal, after a short transient period, both reservoirs have 0 steady state heat current. That's what you would expect at equilibrium when the reservoir temperatures are equal. So our approximate method, this DECIDE method, this approximate method, is capable of reproducing what one would physically expect. So let's now move on to the non-equilibrium case, where with the right reservoir at a higher temperature, 120 Kelvin, than the left reservoir, which is at a temperature of 60 Kelvin. And the values of the remaining parameters are shown here. So now we see, so let's focus on the top panel here. So now we see that after a short transient period, the heat, so here I plot this Q nu here, which corresponds to the heat of either the left bath or the right bath. So the heat of the cold bath or the cold reservoir continues to increase, which is what you expect. Heat is transferring from the hot reservoir to the cold reservoir. So you would expect the heat of the cold reservoir to continue to increase, while the heat of the hot reservoir decreases, as expected. So again, our approximate method is basically reproducing what one would expect physically. And I should point out that our approximate method, or the results of our approximate method, are given by the circles here, while the results of the exact method, sorry, it's the other way around. Our approximate method is given by the solid lines, and the exact method is given by the circles. So you can see that our results are in very good agreement with the exact method. Okay. Also, both reservoirs, so now moving on to the lower panel here. So both reservoirs have a small but non-zero steady state heat current. So you can see that these lines here are not at zero. They're not crossing at zero. One is a little bit below zero and the other one is a little bit above zero. And the error bars are sufficiently small that we can be able to resolve this. So that's what you would expect in the non-equilibrium case, that there would be some net heat transfer from the hot reservoir to the cold reservoir, which is what we see. And again, our results are in very good agreement with the numerically exact results. Okay. On this slide, I compared the decide results, so the approximate results for the steady state heat current, which is shown in red in both of these panels, as a function of the system reservoir coupling, which I called C on the previous slides, for two different sets of bath temperatures, so 60, 120, and 100, 150. So a lower set of temperatures and a higher set of temperatures. And these results were generated with 10 million trajectories. So as can be seen when comparing the decide results in red to the exact results shown in black here, the decide method reproduces the expected turnover as a function of the reservoir system coupling, and they are in good agreement with the numerically exact results shown in black. And we also compare our results to some results of some other approximate methods, and one could see that the decide results actually outperform, or the decide method actually outperforms the other approximate methods that are commonly used to calculate these type of quantities. And finally, I compared the decide results for the steady state heat current, again shown in red, to the exact results shown in black here, as a function of the system's energy gap, this delta. So as can be seen, again, the decide method reproduces the expected turnover, and the results are in good agreement with the exact results shown in black. Now, overall, these results hold promise for decide simulations of non-equilibrium heat transport in more realistic systems. So the non-equilibrium spin boson model is a simple system, but one would like to apply the decide method next to more realistic systems. So for which fully quantum mechanical methods, such as the one that was used here to generate these exact results, would no longer be computationally feasible. Okay, and that's it. I would like to end by thanking the funding agencies and the people that worked on this heat transport research, starting with Dr. Junji Liu, a recent graduate of mine, Dr. Pablo Carpio Martinez, a former collaborator of mine, Dr. Shangyu Xie, and Professor Devira Segal from the University of Toronto. And I'd like to thank NSERC, Alberta Innovates, and CONACYT for funding and scholarships for some of my students, and computing support from WestGrid and Compute Canada. And I'd like to thank you very much for your attention and this opportunity to give this grad talk at YTU. Thank you.
Thank you, Dr. Gabriel. Thank you for this very clear, smooth, and informative seminar.
Thank you.
If we have any questions and comments, Mer will help you. You may either raise your hand or ask your questions by yourself, or you can use the chat box if you don't have a microphone setting. I can read it for you. The thing was interesting while you are writing your questions. I want to ask something. You showed a couple of slides before the lower and higher temperature reservoirs, right, with different settings, and heat current does not goes to zero, you said, with the
yes.
That can you
here? Yes.
Yeah, that's interesting. Can you explain it a little again?
Yeah. So when there's a gap or a temperature gap between the left and the right baths, the second law of thermodynamics, at least in the case of macroscopic systems, this is a microscopic system, would predict that heat would flow from the hot bath to the cold bath.
Yeah.
So there would be a net heat transfer from the hot bath to the cold bath. And this is exactly what we observed at the microscopic level, the single molecule level, that there's a net heat transfer through the molecule from the hot bath to the cold bath. So there would continue to be heat transfer from the hot bath to the cold bath, or the hot reservoir to the cold reservoir. So we see that in the case of the cold reservoir, there's a slightly positive heat current. That means that heat is going into the cold bath. And in the case of the hot reservoir, there's a slightly negative. I don't know if you could see that it's slightly below zero there. It's very small.
Yeah, I can see it. No, if you wait very long, enough time, entropically, they will come to the same temperature level. So there would be no heat transfer.
Yeah, the point is that these reservoirs are sufficiently large that they will always be at their respective temperatures. But you're right. If that was not the case and you wait, then they would reach the same temperature and eventually the heat current would go to zero. Yeah.
Thank you. Any question and comment? I can see some researchers from the field, Ahmet, Çetinkaya. And also at the very beginning, you show us what was that, rubidium?
Yes.
Right? Coherence and decoherence.
Yes.
What is the difference? Like when we increase or decrease the temperature, how do we get the decoherence pattern?
Right. So if the temperature was high in this experiment, you would observe this pattern here on the right. So the temperature really has to be low in order to observe this coherent pattern on the left. And the reason for that is that the so-called thermal de Broglie wavelength becomes larger as you decrease the temperature. So the particles become more wave-like, if you wish, as you decrease the temperature. And as a result, when the particles become more wavelength, or when the rubidium atoms become more wave-like, then they will behave more quantum mechanical, and you get the pattern on the left. While when you increase the temperature, the thermal de Broglie wavelength becomes smaller and smaller to the point where it becomes more or less a particle, and you get the result on the right.
That is more like classical case.
More like classical case, classical diffraction, exactly.
Okay, Ahmet would like to thank you. I guess, Ahmet Çetinkaya, I guess you had a collaborative work with you, right?
Yes. Yes.
Paper.
Yeah. On a completely different area, though.
Okay.
Yeah.
So Nadir Javani from our Yıldız Technical University would like to ask something. Thank you for the nice presentation. What about the maintaining of the coherency for a rather long time in the quantum computing?
Yes, that's a very good point. And actually, that's the deal breaker for quantum computing. If one can't maintain that quantum coherency, quantum computers would be useless. So a lot of effort is being, a lot of research is being done in order to reduce these error rates. And one way of doing that is to keep the computers or the chips or the systems ultra cold. So when you keep the system ultra cold, you can extend the coherence time of, let's say, if you're using ions as qubits or superconducting qubits for the bits. So that is extremely important. So one way is to keep them ultra cold, or other active and passive schemes for protecting the qubits. I'm not an expert in quantum computing, but there are other there are a number of ways for doing that, but that's still a very active research topic, and one of the main, let's say, barriers between making making quantum computing more practical and to increasing the number of qubits in quantum computers.
And Any questions and comments? And about your method, decide, what was that stand for? There is this something coordinate.
Yeah, I could barely remember what it stands for.
Coordinates are shifted or moving. What was that?
Yes, let me go back to it. So this, in hindsight, was not the greatest acronym, but because it stands for deterministic evolution. Yeah, of coordinates with initial decoupled equations. So one of the reasons why we named it this way is because in the other mixed quantum classical methods, the coordinates are evolved stochastically as opposed to deterministically. So we found a deterministic way of evolving the coordinates. So using these equations. So I just show you these equations, but we actually derive these equations. Based on a particular approximation, we were able to derive these equations. So these look like classical equations of motion, but these are indeed mixed quantum classical equations of motion.
Thank you. And there's another question from Seda. If you have microphone setting, maybe you want to read it by yourself, Seda?
I could read, okay.
Maybe she would like to talk.
Okay, sir. Sorry, go ahead, Seda.
Seda'yı açabilir miyiz mikrofon?
Yes.
Yes, Seda.
I wonder that you have said that in the electron transition system, you have used the classical mechanical method and quantum mechanical method. In classical mechanical method part, you have used the harmonic oscillator method model.
Yes.
But I don't understand why you choose this method in order to calculate your electron transition system.
Mm-hmm. Okay, so you're talking about, let me just go back here.
Seda, thank you.
Are you talking about this system, Seda?
Yes, this one.
Okay, so so this is just a simplified model of a single molecule thermal junction. So let me just start with the molecule. So the molecule is basically reduced to a two-level system. So in reality, a molecule has many levels in it, but we just reduce the molecule to two levels, which participate in the heat transfer from the hot bath to the cold bath. Now moving to the reservoirs. So in reality, as shown in the example on the previous slide, these reservoirs could be, let's say, a gold STM tip or a gold substrate. So these reservoirs have some modes in them, some motions. Like in the case of the gold atoms would be, have some phonons, moving through them and so on. So harmonic oscillators are, say, a natural choice for representing those modes. And I didn't show you all the details, but you can actually assign particular frequencies to those harmonic oscillators. And by doing that, you can mimic the real system in which, let's say, in the case of the gold, leads, you can mimic the modes in that gold system. So I didn't go into the details, but you can assign what's known as a spectral density to the harmonic oscillator reservoir in order to mimic those real reservoirs.
Thank you very much.
You're welcome.
Thank you, Seda. Do we have any more questions or comments? I think everything is very clear. So if not, I would like to thank to Gabriel Hanna'ya again on behalf of my university and Graduate School of Science. And I hope you meet you all for the next Grad Talks. Thank you, everyone.
Thank you, Murat. Thank you very much. Bye, everyone. Have a good night.
Have a good day. I guess it's early morning.
Yes. Yeah. Thank you very much. Bye-bye.
Okay, bye. Thank you, everyone. Good evening.
Good evening.